All right, guys. So I did a little research.
Oh boy.
Mary, can I get you to shut that door for me? Thank you.
That we've been told wrong.
So, no. About the phi number. Remember I said there's a little formula you could do for phi numbers? Okay, so I remember the one that Gabe showed me, but I also got another one that might make more sense, but I'll just show you the options. Okay, so this, and I got to be honest with you, it's going to save you a little bit of time and certainly would save you a ton of time on something like if I said find the last 3 digits or the last 2 digits and you forgot that 5 of 100 was 40 or 5 of 1,000 was 400 if you forgot that. But here's what I can tell you. And you might want to copy this down somewhere. So I wrote it out kind of formally. So if you have a phi number, or you're trying to find the phi of a certain number, okay? And that number happens to factor, I'm going to call it a to the m times b to the n times c to the p, etc., etc., etc. Okay? So let's just say you got it into its prime factorization, okay, where this is the prime factorization. Now it has to be prime factorization. Don't leave it as 10 squared. It's not going to help you that way. Then all you have to do to get the phi number is take the original number and multiply it by 1 minus 1 over the A, 1 minus 1 over the B, 1 minus 1 over the C, etc., etc. And you'll notice that the M, the N, and the P don't even matter. So for example, we'll use that phi of 100. Okay, so we already know the answer to this is 40 because I showed you that, right? But since that factors into 4 times 25 or 2 squared times 5 squared, all I have to do to get the actual number is to take the 100 and multiply it by 1 minus 1 over 2. You ignore the, don't even need to worry about the exponents. 1 over 2, and then 1 minus 1 over 5. And that gives you 100 times 1/2 times 4/5. And you can see that 10 cancels with that 100, leaving you 40. And another way you could think about this formula, if you're looking at that formula and going, it's kind of annoying because I still have to do some work. Here's another way you could look at the formula, but that's how I read the formula. Another way you could look at it as, to find that common denominator, aren't I going to have to go A over A and then subtract? So doesn't that basically give me the number times the factor on the bottom and 1 less than the factor on the top? Factor on the bottom, 1 less than the factor on the top. Factor on the bottom, 1 less than the factor on the top. So if you really think about it, going back to that phi of 100, it's probably a little bit easier to memorize this if you think about it, or just understand what to do. Because in the situation, I could just go, 100 times, put the 2 on the bottom, 1 less, put the 5 on the bottom, 1 less, and then simplify. Are you seeing that? So, so something like phi of 120. How does 120 factor? Well, I know 2 goes into that, leaves a 60, right? 2 goes into that, leaves a 30. 2 goes into that, leaves a 15. So what is that? 3 2s, a 3 and a 5? So if that factors into 2 cubed, 3 and 5, what would I do? So 120 times 2, 3, and 5 on the bottom, and 1, 2, and 4 on the top. So you could come in there and go, well, that's a 10 times a 3 is a 30. 30 goes into that 4 times 32. So it's a much quicker way to get your phi number. Now, do you really need it? Most of the time, no, because the number the mod number is something like 12. But even if it was something like 12, it's kind of helpful because what is phi of 12? 12 is 2 squared times 3, right? Right? So all I really have to do is do 12, put the 2 and the 3 on the bottom, 1 and the 2 on the top. 6 cancels with that, leaving me 4. So it beats right now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Canceling all the even numbers and all the numbers that have multiples of 3 in them and then adding them up. It's a little quicker, isn't it? Right? So that's one way to do it. You know what? I don't even know if I'm going to bother with the other way. This is just one more thing and it's not easier. So let me just stick with that. Might make it a little easier. But that'll be a great thing if I ever say something like, what's the blah, 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 this big blah, 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 if you're divided by 36. And you're like, oh, crud, 36. That's a terrible looking phi number, isn't it? Right? But now you look at, oh, 5 of 36 is just 4 times 9, right? So you just go, oh, well, 36, put the 2 and the 3 on the bottom, reduce them by 1, cancel up 12, and you're done. And it didn't take you much time, and you didn't have to do so much writing. Not too bad? Okay. So anyway, I kind of like this. I think this may be what Gage showed me, but that's what I saw on the internet 100,000 times for phi of a number. And again, that other one that was kind of weird. But anybody got a big question about any of these? Of the mod problems that you maybe had some issues with? Were you able to do them? Yep.
I got stuck on number 12.
Number 12. Is that the one where you, yeah, these are just, I'll just go ahead and tell you, they're horrible. I'm not going to give you one on a test. Or if I did give you one on the test, the numbers would work out miraculously not. I mean, it'd be super nice. You know, I mean, it just wouldn't require. And this is the one I think I may have mentioned to you guys that the Hoover guy put as a ciphering question. And I was like, you gotta be kidding me. And after working for a while, I finally pulled my calculator out and I finally got it. And I'm like, there's gotta be a trick to this. Maybe I just don't know something because I mean, over my evolution as a math teacher, there's tons of things I haven't known. I've just sought out. In the olden days, we didn't have the internet. I've been here a long time. We didn't have the internet, so we could look up stuff. So I have a couple of these doctor guys that I know that have their doctorates, and maybe I call them up, and but I called up this guy who does have a doctorate. He's the guy at Mountain Brook now, and he shows me the key. Did I tell you this? Oh, what am I telling you again? Anyway, bottom line is he's like, oh man, my bad, sue me. I was like, sue you? It's on your test. Anyway, so for this, the last 3 digits I can find by dividing by 1,000. Because if you divide by 100 and find the last 2, 1,000 will give me the last 3. Well, that's a horrible looking mod problem. So I'm going to give myself lots of room, but I'm going to need way more room than this. So I am going to ignore this, and I'm going to start that problem over here. So 2315 mod 425. I might even pull out the calculator. Mod 1,000. So I can divide that by 1,000, which will leave me a remainder of 315. And I can divide that by a phi of 1,000, which we happen to know was 400. But if we didn't know that, remember now we have a plan, right? Phi of 1,000. 1,000 is the same thing as what? It's like 100 with an extra 10, right? So an extra 2 and a 5. So it's a 2 cubed, 5 cubed, right? So I would just take the 100, multiply, put the 2 and the 5 on the bottom, decrease them, cancel, multiply. And if I divide 400 into 425, that shrinks it to this. And this is where most of your work will start looking different. At this point, if you do these 2 steps, I'm going to probably give you half credit, right? I mean, because you've done most of the shrinking that you can do. At this point, it's just tedious. It is. It's just tedious. So I look at this and I go, well, crud, what can I do with this? Any ideas? I can't subtract 400. I can only subtract 1,000. And that gives me even bigger number and negative. Anybody? Okay, so let's start with 315 squared. But how many of those would I have? Yeah, don't say 12 and a half. 12 would give me 24 of them plus another what? I mean, not plus, times another what? 315. Okay, that's a good start. So 315 squared, I would have to suck it up. Now, keep in mind, when I multiply 315, all that matters is what? The last 3 digits. So if you were doing this 25, 75, 15, that 1 doesn't matter because I'm going to be dividing by 1,000 and keeping the last 3. Divide a 1, 315, don't forget that 0. And then a 3 into that is what, 945. So none of this even matters. So 5, 12, 225. Are you all seeing where I'm going with that? I can get the big number, but I'm just going to turn around and divide it by 1,000. So it really doesn't matter what's there. When I divide it by 1,000, I'm left with 225. So I replace that with 225. And now I'm here. Anybody got any ideas? 225 squared. And this was a cipher question. But if it's 225 squared, it's really what? 225 squared to the 6th. So I go, all right, let's try 225. So that gives me what? 1,125 for the first one, and then put a 0, and then that gives me 450. And then I put 2 zeros, and that gives me another 450. So 5, 2, 6, blah, blah, blah. Who cares? Because when I divide it by 1,000, I'm only keeping the 625. So that gets me 625 to the 6th. But you get the idea, right? Now, at this point, it might go, well, if I subtracted 1,000, what would I have? That's smaller. Negative 375, and a negative 375 to the 6th is a positive. But it's a little smaller, but it's not that much smaller. It's still a 3-digit number. I still have to suffer multiplying, right? So this is just a tedious problem. So don't expect to see something like that at a test unless it's something like, what are the last 3 digits of 2001, to, the 2007. I mean, maybe something like that. And what happens when you divide that by 1,000 and that by 400? Oh. And that's me checking your phi number, but I'm not going to make your life overly miserable. Or even if I did that, maybe 2012, and you end up with, 2 to the 12, 4096. And then when I divide by 1,000 again, 96. So maybe something that's reasonable, but nothing like this we're not even close, right? We still got to divide into that, and then redo it again, and then redo it again, and then figure out the 315. It's going to be super awful. Don't expect to see that. All right? But you never know. If this was at a math tournament, I'd probably look at it and go, seriously? And then I'd probably log it away in my head that I know how to do it. I mean, I might do the first couple steps and see if I get somewhere reasonable. But if I did the first couple steps and ended up with this, I'm moving on. And I might come back to it if I finished up the test and I look down and I got 25 minutes to kill. But think of the math. There's so many ways to make a little bitty math error. You make one error, terrible. But you won't see that at an Algebra 2 level. That was a comprehensive question I mentioned. Algebra 2 level, it's usually pretty basic stuff. If you know these rules, it will be child's play to you. All right? When we go through some of the old state tests, you'll see it show up every now and then, and you'll go, that's the mod problem. It'll be simpler than anything on this page. All right? All right. Okay, so Let's be flexible. What sounds great to you? Square roots of irrational and imaginary expressions. Strange manipulations. Number of integral factors or sum of integral factors.
Number and sum.
We'll vote. Who wants the one? This is on page 7.
Number of sum.
Square root, the stuff on page 7, square roots of irrational and imaginary expressions. Raise your hand. You got to vote for something.
Or do we torture 6 people and give them that?
1. Okay, I got 1 vote. Strange manipulations. You voted twice. I got 3.
Integral factors is
Number of integral factors and sum of integral factors. Okay, we're jumping to that. We're on page 18.
Number and sum of others just two separate.
They all got to kind of go together.
okay. There's 7. We can do this over the summer, right?
Is this easy or hard?
Yeah, I thought it was in the summer.
Watch it be hard, like the hard.
That should be the hardest thing on that.
Okay, did y'all do that? Y'all didn't print that way, did it?
Nope,
No.
no.
That's weird. No, I don't think so.
No, sorry.
Okay, like it's split here. All right, so every now and then somebody's going to give you a question. They'll say, find the number of integral factors and the sum or the sum of the integral factors. So here's a little something, and I'm doing all of this explanation here, but I'm going to show you a little example and then jump to the why. I mean the how. Okay, so I'm going to give you a small example and show you what they're asking for, and then I'm going to show you what you would do with really ugly problems. So let's just say I said, what is the sum of the integral? I think we're going to start out with the positive integral factors of, we'll start small, and I'll use 60. Okay, so the hard way to do this would be to write out all of the integral factors. Now, you say a factor is something like, oh, well, a factor of that would be like 2, not a multiple, a factor like 2, 3, 5. But what about a half? A half is a factor. Half times 120. Third times 180. Those are all factors. So they would have to say integral factor. If I didn't say integral factor, how many factors are there? An infinite number. Okay? And by the way, if I don't say positive when I say sum, for every positive 2, there's a negative 2 that would also go in there, right? So what would the sum of those be? Always 0. Actually, a question that shows up at tournaments. Find the sum of the factors. No, find the sum of the integral factors of 29,376,000, blah, blah, blah. Who cares? It's 0, right? Because there's just as many positives as negatives. But if they do say positive, the hard way to do this would be this. Well, I know 1 goes in, I know 2 goes in, I know 3 goes in, I know 4 goes in, I know 5 goes in, I know 6. 7 doesn't, 8 doesn't, 9 doesn't, 10 does, 11 doesn't, 12 goes with the 5, 15 goes with the 4, 20 goes with the 3, 30 goes with the 2, and 60 goes with the 1. And now I have to add them. So then I would start adding them up. Now, that is something that it's at least doable. It will not be doable in a reasonable amount of time if my number is 5,280 or 36,425. It's not going to be reasonable. So I want to show you something that just happens to work out here. Look at this 60, and I'm going to write the prime factorization. Now, it factors into 4 times 15, so that's 2 squared, 3, and 5, right? Now watch this. If I take the 2 squared and add it to a 2 to the first and a 2 to the 0, which, by the way, I really don't need 2 to the 0 because 2 to the 0 is what?
1.
So I'm just going to put a 1 there. And then I take the 3, which is 3 to the first, and I add it to a 3 to the 0, which is also 1. And then I take a 5, which is a 5 to the first, and add it to a 5 to the 0, which is also 1. If I multiply this all together, I'm going to get that all added together. Now, why does that work? Because what this will do This, when you start to multiply, and I'll do it slowly, it's a pain, but I'll do it for this small number. What it does is it groups every possible way to have no 2s, 1, 2, or 2 2s, with every possible way of having no 3 or 1 3, and every possible way of having no 5 or 1 5. Check it out. First, I'm going to FOIL this out, and that gives me what? I'm not even going to write 15. I'm going to leave the factors. It gives me 3 times 5 plus 3 times 1 plus 1 times 5 plus 1 times 1. And all of that times this. Now this gives me, when I distribute, what? 2 squared, 3, 5. 2 squared, 3, 1. You with me? 2 squared, 5, 1. 2 squared, 1. And then when I do the 2, I get 2, 3, 5. 2, 3, 1. 2, 5, 1. And 2, 1. And then when I do the 1, I get 3, 5. Sorry, 3, 5. If I'm bothering you at the second, hold on, just hang in there and I'll show you. 3, 5, 1, 3, 1, 5, 1, and 1. Now watch this. What is, that's there. There's my 2. There's my 3. There's my 4. There's my 5. Oh, there's my 6. There's my 10. There's,
It's the second one.
oh, there it is. There's my 12. There is my 15. There is my 20. There is my 30. Nope, that's 60. There's my 30. And then there's my 60. So didn't this process give me all of the terms? Now, I would still have to add them together here, which puts me in a miserable state, right? Well, I'm not going to do that. I'm just going to do this to add them together. 4 and 2 is 6 and 1 is 7. 3 and 1 is 4. 5 and 1 is 6. 24 times 7 is 168. I'm done. So to find the sum of the possible integral factors, I do the prime factorization, and then whatever I get, I start with that particular factor, and then I just add the same factor with one less power until I finally hit the 0 power, which is just 1. But then instead of FOILing it out, which is miserable, I don't need to know the numbers, do I? I just need to know the sum. So all I would have to do with the sum is just add these fractions and multiply together. Not too bad? Okay, and then we'll do practice these. The second question you get asked is this. How many positive integral factors? Dang it, I should have erased that. Can I get Yes. How many positive integral factors? Now, we just saw all of these groupings, right? How many numbers do you have here? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How did I really get 12 terms? Think about it. Sort of. I heard 4 times 3. It's what? 3 times 2 times 2. Each one of these got multiplied in, right? There were 3 things here that had to multiply through. there were two things here that had to multiply 2. There were two things here, two actual items is what I'm saying, right? When I multiplied all of these 3 by all of those 2, it gave me 6. And then when I multiplied all of those, actually, I didn't do it that way. I multiplied those 2 by those 2 and got 4, right? And then I multiplied those 4 by those 3 and got 12. Well, if I say not the sum of, but if I say how many positive integral factors are there, where does that 3, 2, 1 come from? Think about it. Why were there 3 here? Because I started with 2 and went to 1 and then 2 to the 0, right? So that 3 is just 1 higher than that. This 2 is because I started with 1 and went to 3 to the 0. So this 2 is 1 higher than that. 1 higher than that. So if I want to know how many, all I got to do is say, well, whatever the prime factorization was, if I increase each of those by 1, that's how many terms were in these expressions, and I can multiply them together and get 12. And I don't have to know the terms. I don't have to sum the terms. All I had to count them. And I certainly didn't have to find them and count them. Are y'all tracking with me there? Now, what if I don't say positive and I say how many integral factors? That times 2, because there's just as many positives that are integrals that would go in there as there are negatives that would go in there. So double it. Not too bad? Let's see. Now, at the end of the day, all you got to know how to do is how to do it, right? At the end of the day. So let's just look at a couple of these. Determine the number of integral factors of the number 360. This is probably your page 19 at the top. I don't know what's happened to my PDF here. So you're going to have to do the prime factorization of 360. I did it for you. It ended up being 2 cubed, 3 squared, 5. So what if I said, first question, find the sum of all of the integral factors. What would you say?
0.
0, because it's just as many positives or negatives. They're going to cancel each other out. What if I say find the sum of the positive integral factors? What do you do with the 2 cubed? You go
2 cubed plus.
You go 2 cubed plus 2 squared plus 2 to the first plus 2 to the 0, which is 1. And then what do you do with the 3 squared? 3 squared plus 3 to the first plus 3 to the 1. 3 to the 0, which is 1. And then what do you do with the 5? 5 to the first plus 5 to the 0, which is 1. And in theory, to find the sum of them, you would have to FOIL the crud out of this to find all your individual terms and then add them together. But we don't have to do that because we can literally come in here and add this, which is 15, add that, which is 13, add that, which is 6. And then I'm just going to do some clever math here and go, I think that's right, 8, 10, 14, 15, 9, 10, 13. I'm going to go 6 times 15, which is 90. And then 90 times 13 is what? 1170? And it probably says that down there somewhere. Well, I'm doing the problem right. Isn't it worked out?
It is. Yeah.
Somewhere down there somewhere.
On the next page.
Next page. Okay. Now, if I say how many integral factors, and it didn't say determine the number of them, if it said how many, then what? You take the prime factorization and you look at each of the powers, which are what? 3, 2, 1. You increase them by 1 to 4, 3, and 2. You multiply and you get 24, but 24 is how many positive integral factors. To find the total number of integral factors, you double it, and there'd be 48 total. And you really got to be careful and read. Is it saying sum? Is it saying sum of the positive? Is it saying how many? Is it saying how many positive? I guess I could ask how many negative, but usually it's not that. It's usually the positive or just how many. So with all that in mind, if you scroll on down to the work, let's take a look at a couple of these. This should be your page 21, I think. So 83/16. Now, guys, you're going to have to suck it up and divide, right? My advice is to do upside down division. So I always start with prime numbers. Don't divide like a 10 into this, or you're going to think 10's a prime number. It's going to mess you up. Maybe you don't, but you might. So if I divided a 2 into that, I get 4, 1, 5, 8. Right? Divide another 2, 2, 0, 7, 9. That right there adds to 18. I know 3 goes into that. 3 goes into that. 6, 93. 3 goes into that. 2, 31. 3 goes into that. 77. And 7 goes into that. 11. So I've got 2 squared, 3 squared, 7, 11. My question is, how many integral factors? 1, 2, 3. 3 cubed. Look, I just missed it because I'm not being careful. So 2 squared, 3 cubed, 7, 11. So how many integral factors? What do I find first? How many positives? And then double it for the total. Positives, negatives. So what do I do to find how many? 3, 4, 2, 2. So I'm going to multiply 3 times 4 times 2 times 2. 12 times 4. So there's 48 positives. Therefore what? 96 total integral factors. Now, if I give you, say, I'm just jumping around here. Look at number 4. So number 4. Now, something like number 4, where it's got 100 in there, I might just go, well, I know 100's a 4 times 25. So I'm going to do this just to make my life a little bit. I don't want to keep dividing 2's into that. So I'm just going to make that 108 and go ahead and say, all right, I've already got a 2 squared, 5 squared. So 2 goes into the 108, 54, 27, and we know 27's 3 cubed. So what do I end up with? 2 to the 4th, 3 cubed, and a 5 squared. But do whatever you got to do, right? You be you when you're doing your division. Hopefully you'll be okay on that. So it says how many yes. That's me getting rid of the double zeros at the end because that's 100. That's times 100. So I'm thinking about it as 108 times 100, and I already got the 100 factored in my head. That's like burned in there. If you don't, it's 4 times 5, right? 4 times 25, or 2 squared times 5 squared. So I just took out that 100 and then worked on the 108 to get it factored. So how do I find out how many positives? What do I do? I look at the x. It's all about these, right? So 5 times 4 times 3. So 60. Do I double it? No, because that's how many positive integral factors, just the positives. I only double it when I don't see the word positive. And then sum. All right, let's look at number 7. Well, look at number 9 because we've already got number 9 factored. Right? So what did number 9 just has 1 less 2 and 1 less 5. Right? No, it's the exact same thing. Sorry. What did we have here again? 2 to the 4th. So 2 to the 4th, 3 cubed, and 5 squared. So this one said, what is the sum of the positive integral factors? So it said positive. It just said sum of the factors, 0 them out. Or sum of the integral factors, because positives and negatives would add together and cancel each other. But it says sum of the positive ones. So what's my trick? You start with what? 2 to the 4th, 2 cubed, 2 squared, 2 to the 1st, 2 to the 0, which is 1. Then I go to 3 cubed, 3 cubed, 3 squared, 3 to the 1st, 3 to the 0, which is another 1. And then I go to the 5 squared, 5 squared, 5 to the 1st, 5 to the 0, which is 1. And again, why do I do this? Because if I were to FOIL it all out, what does this do? This gives me every possible combination of none through 4 2s and none through 3 3s and none through 2 5s. It assigns every possible scenario. I don't want to know those scenarios. Now, hey, if I ever wanted to know the factors of 10,800, you can do it this way. Literally, that times that. FOIL all this out, and then FOIL all that, but don't add anything together. And you would see all of the actual factors. That's a way to do it, if you wanted to. I mean, I don't know. I mean, it beats going, oh, does 2 go in there? Does 3 go? I mean, it works. But we don't need to do that because we can say, well, what is this? 16 and 4 is 20. 8 and 2 is 10. That's 30, 31. 27 and 3 is 30. 9 and 1 is 10. That's a 40. 25 and 5 is 30 and a 1. And I just got to multiply that together, which I don't know. Gives me a big number, 38,440. But at least get to there and write it out, right? And definitely show me your setup. And don't add these. Remember, you're adding each the stuff on the inside, but then you're multiplying at the end. Not too bad. Well, that was too easy. We got too much free time. We get to do something else now. Oh, no, we're not done. Forgot about these. So right there, what would you do on number 10? What is the sum of the integral factors? 0. Okay, now, what about this? This is where they become tricky. All right? So what is the smallest positive integer that just happens to have 15 positive integral factors? Number 11. What is the smallest integer? So there's a number out there. It's an integer. It just happens to have 15 positive integral factors of it. What's the number? Well, let's think backwards. How did I find positive integral factors? I did a prime factorization. Then what? I increased the powers by 1. And then I did what? Multiplied them together. And I got my answer. Well, I'm going backwards now. Now I'm telling you that this mystery number has 15 positive integral factors. Well, what numbers would have multiplied to give me 15? 3 and 5 or what? Okay, so let's start with that. 3 and 5 or 1 and 15 would have multiplied to give me 15. True. But wait a minute. Remember the process. Hold on. I would have added 1 to get to this. So that means, remember the way I did it? I did the prime factorization. I took the powers. I added 1 to them and I multiplied. We're going backwards. So now I have my number. I unmultiply. I decrease by 1 to get the powers. Or and then I've got to put in what the bases would be to give me the smallest number. Now, what would you like to choose? If I'm trying to get the smallest one, by the way, I could put any prime number in there and get a number. Any prime number, any prime number, any prime number, any prime number, as long as there are different prime numbers here and here and here and here. I can do any one I want, and I will get a number that has 15 positive integral factors. I want the smallest. So what's the smallest prime number you can have? 2. Where do you think I want to put the 2? With the biggest power. Because if I don't, and I put the 2 with the smallest power, now the 3 is going to be with the biggest power. And if there's more than one, maybe the 5 will be there, right? So why not put the 2 with the biggest power, and then I can put the 3 with the smallest one. 2 with the biggest, 3 with the smallest. Now you can see there's no way that's going to work out for you, right? I mean, 2 to the 14th is way bigger than 16 times 9, 144, right? So this one is huge, right? It is not smaller. I got to go with this, which ends up giving me 9 times 16, 144. So 144 is the smallest integer that happens to have 15 integral factors.
Where'd you get like a 3 and 2?
Okay, remember the process. What if I started you with 144? If I start you with 144, you do the prime factorization. 3 squared, 2 to the 4th. Then you take the 2 and the 4 and you increase them by 1, right? Sorry, 3 and 5. And then you multiply it together and you get 15. I am going backwards. I am getting 15. I'm factoring it, 3 and 5. I'm decreasing them by 1 to get the powers, 2 and 4. And then I'm assigning bases. I don't know what the bases are. They could be anything. But I want to make it the smallest number possible. How would I find you using too many pronouns? Don't use it. Don't use those. How would I do what? Use 2 and 3?
Yeah, how do you like find it?
Well, what else would you use? If I use 3 and 5, are the numbers going to be, is that final number going to be bigger or smaller?
Is it always going to be 3 and 2?
I'm going to start with 2, then I'm going to move to 3, because I want to make it small. If I use 3 and 5, is it smaller? It's going to be bigger, right? Isn't 3 to the 4th bigger than 2 to the 4th? And isn't 5 squared bigger than 3 squared? So I want to use the smallest numbers possible. They got to be prime. So I'm going to start with 2, then go to 3. If I need another one, I'll go to 5. If I need another one, I'll go to 7.
Is it just like guess and check? Or like how do I? This one we're gonna have to find how to 3 and 2 because they're the smallest prime number.
Because I'm trying to get a smaller number. Like if I use 7 and 11, am I going to get my smallest number, or am I going to get a massively big number?
So it's always gonna be 3 and 2 for any problem.
No, because sometimes my numbers aren't 3 and 5. Sometimes they're 3, 5, 4, 6. And that means I need 4 prime numbers for bases.
Can you go from the smallest prime?
I'm going to start with the smallest primes and move up as I need them. But if I only need 2, I'm going to use 2 and 3.
Okay.
If I need 3, I'm going to use 2, 3, and 5.
Oh.
Because I want to make my total final answer small. So if I don't start small, I'm not going to end small, right? Okay, let's try another one. What if I said this? What's the smallest integer with 10 positive integral factors? Well, that 10 came from what? 2 times 5 or 1 times 10. And that 1 and 10 and 2 and 5 were what? 1 more than the powers associated with these prime numbers. So that if it's 1 more, then this would have been a 1 and a 4, which would have been the exponents. Here it would have been a what? 0 and a 9. And since there's only 2 numbers that could be bases, and I want to keep this small, I'm going to start with 2 and 3, right? But where would I put the 2? I'm going to put it there because 2 to the 4th times 3 is much smaller than 3 to the 4th times 2. So I'm going to do that. Same thing here. But you can see right there, 16 times 3 is 48. That's 512, clearly not smaller. So 48 is the smallest positive integer that happens to have 10 integral factors.
Is it always going to be the one closest to, like, that are like closest to each other?
I love that y'all's brains are thinking. There's a trend that way, yes. And clearly, 110 is going to rarely be a good option any more than 115 was, because you're going to end up with such a huge power on that 2. It just doesn't typically work out. So a lot of times I don't even bother checking those, like if it was a ciphering question, right? So normally it is, but not always. Because sometimes, like you'll see as we go through these, I could, like the number 12, for instance, could be 6 and 2, could be 2, 2 and 3, could be 1 and 12, right? Could be 3 and 4. There's lots of different things that could give me 12. And sometimes you just have to write them all out and play with them. All right, now look at this. This one, what's different about this one than this one?
Total factor.
Well, I didn't say positive. So what is that really saying? That I have 6 positives. Oh, well, if I have 12 total, then that means I really only have 6 positive integers. 6 positive factors. Well, if that's the case, I can go, well, what multiplies to give me a 6? A 1 and 6, or a 2 and a 3? And if 1 and 6 were the things I multiplied together, where did they come from? 0 and 5 would have been the powers, right? Or 1 and 2 would have been the powers. And then if I plug my 2 into the highest one and 3 into the other one, I get that's a 32 and that's a 12. And like Quinn was thinking, it normally are the factors that are closest together when there's only 2 options. Yeah.
Instead of 12, we had an odd number.
You wouldn't be able to do it. Because you won't have that, right? If you're going to have this X number of positives, you're going to have X number of negatives. So it's always going to be an even number. Yes.
So for all the math problems, when it says division, so that means like factors or
When it says what now?
like it says,
14.
yeah, like 14 for the they're all they all say like how many positive integrals.
Yeah, if something divides into it, it can be a factor, right?
Okay, so
Although right here, I made a note about this somewhere. Hold on. Is the bell about to ring on us? Okay, right here. Factors are generally assumed to be positive, whereas divisors could be positive or negative. That's something to consider. Hey, before the bell rings, let me just show you one last one right here. Which one was it? Remind me, I'll talk about it tomorrow. Do the best you can on this.
finish the problem.
Yeah, finish them up. You have a good one.
This is on Wednesday, right?
Yes.
So are we reviewing tomorrow, or are we gonna learn more?
We're going to learn one more thing, I think.
We have one on Wednesday.
Yep. Not too bad, man. How about you?
Enjoying your day?
All right.
Has your class has been distracted by the rankings, which is
Golly, no. Y'all were like weird.
well, it started coming down like crazy. It's like I don't know. I can't not look at it. But you should see our film studies class. It'll start raining and there are like 2 or 3 guys in like sophomore class. They'll just go over and stand by the window and watch it.
So funny to me. It's like people when they're driving, it starts raining and they suddenly go like 10 to 15 miles an hour slower. I'm like, dude, you've got tires. It's not like it's a bed of oil.
I literally driving back from. Have you heard of Young Life?
Oh, yeah, I was a big Young Life kid.
Oh yeah, I am too. I did work crew. I did summer.
Where?
South.
I did a work crew at
I drove there by myself. Down by
Where's that?
Just walked by Orlando. Yeah, so I drove there by myself, and then on the way back, it was like a hurricane, like bad. And I was driving so fast.
Oh, now it's crazy. I can't see. I'm going to slow it down, but it's just like rain. All right, man. Have a good one. Garza is back. You survived the quarantine?
I'm gonna look at my phone and it's just like.
Oh, I got and then they couldn't have
Yeah, man.
I need the book called the book for
Not that one. So the only thing you've missed on this,
I was in the Google Meet yesterday, but I
the
was
modular stuff.
I can only kind of think because that was really fuzzy. I could barely see it because the camera.
No, it's not great.
It's digital onto digital, so
It's
it's hard
something,
to
it's not
see.
great.
So I kind of picked up on it a little.
We're gonna do a little bit with it before we get started. So see if that helps a little bit.
Yeah.
I believe it's 2 o'clock.
All right, guys, you ready? Okay. I mentioned the little phi number, that there's a trick to finding it.